Hello viewers, welcome back to the course on scientific computing using MATLAB. So, today we will going to discuss the another method that is called that how we can find the eigenvalues, because in the previous lecture we have seen that the eigenvalues play a very important role in the convergence of the iterative method. So, now the next question is that how we can find the eigenvalue using the numerical computation. So, now from the previous one we found that the iterative method like Gauss-Jacobi or Gauss-Seidel or other methods, they are dependent on the eigenvalues. The rate of convergence involves spectral radius. So, the question comes that how to find the eigenvalues of the matrix. So, the next topic is how to find eigenvalues of a square matrix that is A, that is n cross n. Because we are involved with solving the system Ax is equal to B, and then we have to find what is the eigenvalue of this n cross n system. We know that the eigenvalues can be found analytically as Ax is equal to lambda x, where x is not equal to 0. Then in that case we say that this lambda is a eigenvalue of matrix A, and this x is called corresponding eigenvector. Now I want to find first what is the eigenvalue and then the eigenvector, and then we know that how we can find this one. Now if A is 3 cross 3, then we can find eigenvalues analytically. Analytically means that with the pen or paper I can find the Cartesian equation and then we can solve this one. Maybe for 4 cross 4 it is quite difficult. And then from A 5 cross 5 and so on, so I can say that it is very hard. Or even impossible. So, now to find out this one we take the help of numerical computation. So, to deal with this one, that how to find the eigenvalues of the matrix, there is a method called power method. So, power method is a iterative method. So, this is a iterative method. So, now how we can do with this one? Suppose I have a matrix A that is n cross n matrix. Now, what I do, because this is iterative methods, so I start with the initial x naught. So, initial x naught means this is my initial guess. So, that is my initial guess x naught. Now, what I do? I will take A x naught. So, I will get another vector, and that another vector I call it maybe y naught, right. So, in this case what I do is that this y naught is a vector. So, now I reduce this vector into the normalized form. normalized vector. So, whatever the vector y0 I am getting, I will call it normalized vector. So, what is the meaning of normalized vector? Suppose I have a matrix like 1, 2, minus 1, 0, suppose this is my matrix and I start with the process 1, 1, then I will get the value, this will multiply and this will add. So, this is 3 and this will be 1 and this will be minus 1. So, now in this case this is the element with the highest magnitude. So, in this case what I will do, I will take 3 common from this. So, this will be 1 and this is minus 1 by 3. Now, the highest value, highest component in this vector is 1. So, this vector is called normalized vector. Does not matter what is the sign, because we want the highest in terms of numerical value or in the magnitude value. So, that this vector becomes the normalized vector. Okay. So, what do we do that? We make it x naught. So, this x naught, this y naught. So, what I do that in the y naught, I will take this element common and then I will make this x1 and that I will call it c1. So, what I am doing here? Now, from this vector I have taken this element, the highest element common. So, I call it c1 now and then the remaining vector becomes x1. So, x1 is my normalized vector. Okay. So, from here I can say that my x1 will be 1 over c1 y naught. So, that is my the normalized vector in this case. Now, from here what I do that, now I put next step, I will put ax1. So, in this case what will happen, I will put the ax1, from here I will get y1. Now, with the help of y1 I will reduce this one into c2 x2. So, I will keep doing like that. Then from here I can say that after k steps, because after one step I will get ax naught is equal to c1 x1. So, from here I will get a x1, in the after 2 step I will get ax1. So, after k step I will get ax k minus 1, that can be written as ck xk. So, from here I can write this one, where this is, that you have to keep in mind that this is a normalized vector. This is also normalized vector. So, now from here you can see that I am getting this type of algorithm, that is ck xk. Now, if you just compare with this ax is equal to lambda x, now you can see from here that if as k tends to infinity, that after many iterations if xk minus 1 and xk are same means they will take that the difference between these L2 norm and that norm is less than the required tolerance is almost same, which implies that the limit k tends to infinity ck will tends to lambda. So, this will tends to lambda and then my xk tends to the corresponding eigenvector. Okay. So, that is the process of the power series method. Now, before that one. So, there is one more term we want to define, that dominant eigenvalue. So, what is the dominant eigenvalue? Dominant eigenvalue means, suppose I have a matrix n cross n matrix, and now from the linear algebra we know that if we have a n cross n matrix, then we have a n number of eigenvalues. So, suppose I write lambda 1, lambda 2 up to lambda n, this is the n eigenvalues corresponding to this matrix. These eigenvalues may be complex also, does not matter. Now, if we choose lambda, any lambda ith value, taking the magnitude, that is maximum among all lambda i's, I can call it k, among all i's, then this is called the dominant eigenvalue. So, we call it in the terms of magnitude, maximum of all lambda i's in terms of magnitude. Then eigenvector, that is xk, corresponding to lambda k is called dominant eigenvector. So, that is called the dominant eigenvector. So, now we are ready to apply that the power method. So, this is the power method we are going to define now. Power method. So, assuming that the matrix A, that is n cross n matrix, having n distinct eigenvalues. So, that is the condition, that we are dealing with n distinct eigenvalue, because we know that the eigenvalue may be repeating also. So, that we are not keeping in mind, we are having the n distinct eigenvalues. Now, and we know that if we have n distinct eigenvalues, then which implies that we have n linearly independent eigenvectors. So, we have now lambda 1, lambda 2 up to lambda n, these are n distinct eigenvalues, and I take it V1, V2, Vn, or we can take this as x1, x2, xn. So, these are n linearly independent. So, this is Li, I can write as Li eigen vectors. So, these are there. Now I know that this is the linearly independent eigenvector. So, let we choose without loss of generality that lambda 1 is the highest one. So, I can call it lambda 1 is greater than lambda 2 all lambda n, because they are n distinct eigenvalues. So, we could call it. Now, if x naught is chosen appropriately, then the sequence xk. So, this is a xk I am writing in terms of a vector, because this will be vector definitely. So, this is x1k, xnk, where k is 0, 1, 2 and so on, and ck generated recursively as a xk is equal to yk, axk is equal to yk, which implies my yk, my xk plus 1 will be 1 over ck plus 1 yk, where the ck plus 1 is equal to xjk, suppose I take, and that xkj is equal to maximum of xik, where I is from 1 to n. I already told you that it should be the maximum value, and that maximum value I will take common, that is my ck, as we have discussed here. So, this is basically my ck, and that is the maximum value. Then the sequence will converge to the dominant eigen value, that is lambda 1, and eigen vector, that is x1 respectively. So, that is the limit k tends to infinity, the xk will converge to x1, and limit k tends to infinity, ck will converge to lambda 1. So, this is my statement of this one. I have already explained that for a given problem how we can implement this power method. So, that is the statement. Now, we can do the proof of this one. So, proof is quite easy. Now, given that x1, x2 up to xn are linearly independent vectors. Now, from here I can say that if I choose any vector x naught that can be written as a linear combination. So, I call it a1 x1 plus a2 x2 up to an xn. So, I can write this as a linear combination, because these are the n vector, linearly independent vector. So, any vector which is of dimension n can be written as a linear combination of this one. So, that is my equation number 1. So, where x naught, so x naught is initial guess, So, that is initial guess we are going to start with. Now, I apply the matrix. So, pre-multiply equation 1 with A, the matrix n cross n matrix, whatever the matrix I am taken. So, I can write it as A x naught can be written as A a1 x1 up to a n x n. So, this matrix I can take inside this common, because a1 is a constant. So, I can write this as a a1 a x1 plus a2 ax2 and up to an axn. So, this one I can take from here. Now, the x1 is the eigenvector corresponding to the eigenvalue lambda 1. So, from here I can write that this should be equal to a1 lambda 1 x1 plus a2 lambda 2 x2 up to an lambda n xn. So, this one we can write from here. So, from here I can write this one as, now this is my ax2. Now, from here I know that this ax2 is equal to y0. Now, I know that in the y0 I will take the factor ck common. So, what I can write from here, this one I can write as 1 over c1 into y naught can be written as a1 lambda 1 x1 by c1 and an lambda n xn by c1. So, I am dividing the whole thing by c1. From here, this I know that becomes x1, because we already know that this become x1. So, from here I can write that x1 can be written as, now I can write this as, so from what I am doing now, I will just take the common lambda 1 over c1 from all. Now, I will get from inside, I will get a1 x1 plus a2 x2 lambda 2 over lambda 1, I will get this value, and so on. In the end I will get an lambda n over lambda 1. So, this one so c1 I will just take common, and I will take lambda 1 also common from all this. Now, I will get from here, so this is again I can apply this one. Now, I will again, so I can write as 2. Now, again apply multiply. So, again multiply, pre-multiply with respect to a. So, I will get a x1. So, this is lambda 1 over c1 is a constant. So, I can take common, and from here inside I can write as directly I can write now a x1 plus a2 lambda 2 over lambda 1 a x2 and so on an xn is also there. So, it will be a xn into this factor. So, this one will be equal to an lambda n over lambda 1 a xn. Now, from here I know that this a x1 is again the lambda 1, this is lambda 2. So, this is lambda 1 x1, this is lambda 2 x2, this is lambda n xn. So, from here I can write this as lambda 1 over c1, and then this is a1 lambda 1 x1 plus a2 lambda 2 over lambda 1 lambda 2 x2 and an lambda n over lambda 1 into lambda n xn. Now, again I can take this lambda 1 common, and from here I can get a x1 will be what? That will be y1, and y1 I take the common factor. So, this will be equal to c2 x2. So, now from here I can write that my x2 will be lambda 1 and again lambda 1 I am taking common. So, square and it will be C1 C2 because this factor is I have taken this as a common. This is the highest value we are taking to make this vector as a normalized vector, and from here I can write this as a again a1 x1 plus a2 lambda 2 over lambda 1 and lambda 2 over lambda 1 again. So, it will be square and then an lambda n over lambda 1 square x2 xn and so on. So, if we keep doing after k iterations, so first iteration I will get x1, in the second iteration I will get x2. So, after k iteration I will get xk. So, it will be lambda 1 power k c1 c2 up to ck and this will be a1 x1 plus a2 lambda 2 or lambda 1 power k x2 and an lambda n over lambda 1 power k xn. So, this is we are finding. Now, from here, now if k tends to infinity, then let us see what will happen. Then in this case we know that, so all this factor if you see, then this factor if you see lambda 2 lambda 1, now if you see then this is very less than 1 in magnitude. So, I can take the value this one. Similarly, lambda n over lambda 1 all this value power k. So, this is also less than 1, right. From here I can see that now if I chosen lambda 1, so this is the condition we have taken that in magnitude its value is 1. It may happen. So, let us see what will happen. Suppose I take lambda 1 is equal to minus 8, suppose it is minus 8 and lambda 2 is suppose 4 and lambda 3 is suppose minus 2. Then what will happen? Lambda, so this in magnitude this is the highest value. So, I will take lambda 2 over lambda 1. So, it is 4 over minus 8, this is minus 1 by 2, right. Now, lambda 3 by lambda 1, so it is minus 2 by minus 8, so it is 1 by 4. So, that is value less than 1, this is also less than 1 in magnitude. So, this value is the in magnitude less than 1 and this value is in magnitude less than 1. Now, what will happen if I take minus 1 by 2 power k? So, in this case this will be minus 1 power k and then 1 over 2 power. Now, if I k tends to infinity, then I know that this is going to be 0. So, from here I can say that this factor in magnitude also going to be 0. So, if I put this k tends to infinity, from here I can say that limit k tends to infinity x k and then I put the limit again. I take the limit on both sides. So, this will be lambda 1 power k c1 c2 up to ck into a1 x1. So, this one I can now remove from here. So, from here I can write that this is a1 x1 plus a2 lambda 2 over lambda 1 power k x2 and so on. And now we also assumed that these matrices are distinct, these eigenvalues are distinct and real also, but if it is not real then we have to take the magnitude. So, in that case we can take the magnitude of this one when the eigenvalues are complex. Okay. Now, if you see from here, then I can write from here that the limit k tends to infinity x k, and on the right hand side this tends to 0, all this term tends to 0. So, from here I will get this will be equal to a1 x1, this c1 c2 up to ck. So, I will left with only this limit k tends to infinity, I will get only a1 lambda 1 k x1 by c1 c2 up to ck. So, this factor I will get. So, this is into x1. Now, from here also I know that on the left hand side it is also converging to s1, because we know that whenever we will get a x1 is equal to lambda 1 x1, only then the method will converge. So, this is the same eigenvector. So, from here I can say that this implies that as k tends to infinity, this vector limit k tends to infinity a1 lambda 1 power k c1 c2 up to ck x1 should converge to x1. So, that implies that limit k tends to infinity a1 lambda 1 k c1 c2 up to ck should be 1. Now, from here this is my condition. Now, the same I can write from here limit k tends to infinity a1 lambda 1 k minus 1 over c1 c2 up to ck minus 1, that should be always, it should be equal to 1, because I am just in place of k I am putting k minus 1. So, that is it. Now, I will get 2, so I call it 3, I call it 4. So, now I am dividing 3 by 4. We will get limit k tends to infinity. So, I will get a1 lambda 1 k over c1 c2 up to ck multiplied by a1 lambda 1 k minus 1, and it will go at the numerator c1 into c2 up to ck minus 1, and that should be equal to 1. So, this will cancel out, this will cancel out with this, and this will cancel out with this. So, from here I will get the limit k tends to infinity lambda 1 over ck, that should be equal to 1. And from here I can say that the limit k tends to infinity ck will be lambda 1. So, that is my convergence of this one. So, if my vector is converging to x1, then that x1 is the dominant eigenvector, then the eigenvalue ck will converge to the lambda 1. So, that is the proof of this power series theorem. So, let us stop today here. So, today we have started with the power series method to find the dominant eigenvalues and the dominant eigenvector. So, I hope you have enjoyed this lecture. We will continue from the next lecture. So, thanks for watching this. Thanks very much.